Welcome, dear Recipe interns, mentors, and all spectators. As the team ALA04, we're delighted to perform a presentation of the beat detection algorithm designed for the early diagnosis of diseases. If you're all ready to dive, let's start. Established by three Turkish high school students, our team didn't just flourish its academic background but achieved to earn enough courage to approve complex scientific phenomena or to constitute a reliable working environment where each of us can both appreciate one another's graces and forthrightly give feedback to each other for circumstances to be improved inside of the project. Therefore, before we get into our system, we'd like to share our introspections and insights in terms of our personal progress we made throughout the process. Starting with me. I am Arda Bora Karahan, a junior from Diyarbakır Bahçeşehir College, Science and Technology High School. So far, I've written physics-based research papers with prestigious programs. And this year, I also got various awards from institutes like Conrad Challenge or Earth Prize, accomplishing all these recognitions with strict and comprehensive plans I super rarely change or postpone. In this respect, my studies are always so secure. However, this has completely changed within my SIP journey, starting with the decision of which SIP will be carried remotely for international students. Thus, while I was going to study in an astrophysics class, I landed up in an electrical engineering group where I had very limited knowledge. First, being unable to study in a project that I'm deeply interested in, and then being obligated to try understanding complex topics that I'm not an expert at, were kind of frustrating. However, challenging myself in such a profound topic with a polymath group and getting out of my academic comfort zone really improved me for successfully adapting to sudden changes and soon have progress in a topic that I have no deep knowledge.
Hi everyone, my name is Bilge, and I am a senior from Edirne Süleyman Demirel Science High School, located in the northwestern part of Turkey. I am deeply passionate about mechatronics, especially in the areas of computer vision and embedded systems. I love solving real-world problems using technology, creativity, and design thinking. I'm also an aspiring entrepreneur, focusing on developing smart solutions for mobility and building mobile applications in the automotive field. Beyond technology, I am always eager to try new sports. I am a cyclist and equestrian, and I also compete in badminton, orienteering, and korfball. SIP gives me the opportunity to explore bioengineering, a field I was previously unfamiliar with. Through this program, I have not only gained a basic understanding of the area, but also started to explore what kinds of innovations can be integrated into bioengineering and how they can be applied in real-world scenarios.
Hello everyone, I am Miran Deniz, a sophomore at Diyarbakır Bahçeşehir College Science and Technology High School. I am deeply invested in computer science and math, exploring concepts outside of the high school curriculum. My role in this project was working alongside Bilge and Bora to develop our central algorithm. Applying our code to the project's biological and physical aspects was a fantastic challenge, as it pushed me to not only strengthen my existing skills in libraries like NumPy and Matplotlib, but also to learn powerful new tools on the fly, like Tkinter and OpenCV. Outside of academics, I enjoy chess, guitar, and biking. That concludes our introduction. Now let's show you how all this work came together in our project.
ELISA, short for enzyme link immunosorbent assay, is a widely used medical test that detects specific proteins, like disease biomarkers, in blood samples. Its working principles as follows. A sample is added to a surface coated with antibodies. If the target protein is present, it binds. Then a second antibody creates a color signal showing how much of the target is in the sample. A bead-based version of ELISA replaces flat surfaces with thin fluorescent beads, which allows more efficient multiplex testing, especially useful when sample volume is limited. This method is for in early-stage ovarian cancer.
Inspired by this system, our project focuses on a new way to read the results using image processing. Instead of measuring the average signal from the entire sample well, we use a microscope to capture a wide-field image of the bead population within that. Our algorithm then computationally identifies and counts each distinct fluorescent spot in the image to quantify the target biomarker. This spot count allows us to classify the sample as positive or negative. providing critical data that aids in the diagnosis process. Now, let's take a deeper look at the step-by-step process or algorithm follows to achieve this.
Our analytical pipeline begins with the crucial first step of image loading. We use the OpenCV library in Python to load the raw 12-bit image captured by the microscope. It's absolutely essential to read the image in unchanged format to preserve the full dynamic range of 4096 intensity levels. This ensures that no subtle data which could represent a faint biological signal is lost before our analysis even begins. This step guarantees we are working with the highest fidelity data possible, directly as it was captured.
Once high fidelity is loaded, our next step is computationally isolate the area where the reaction occurred. We achieve this by applying a circular mask known as a region of interest or ROI. The mask focuses our analysis exclusively on the circular well, effectively eliminating the surrounding background and any potential interference. By isolating the well, we create a clean, standardized area for analysis, which is fundamental for the subsequent steps of signal segmentation and counting.
Now that we have a clean, focused image from our preprocessing, the next critical challenge is to computationally distinguish the bright fluorescent beads from the darker background. Our algorithm achieves this using a core image processing technique called intensity thresholding. It's a simple but powerful concept. We define a minimum beat intensity value, a specific brightness cutoff. Our algorithm then examines every single pixel within our circular region of interest. If a pixel's intensity is above this threshold, we classify it as part of a beat. If it is below, we classify it as background noise. This process instantly transforms our detailed image into a high contrast binary mask. As you can see here, the result is an image where only the pixels bright enough to be beats retain their green signal, while everything else is rendered completely black. This step is fundamental, as it effectively isolates all the potential beats and sets the stage for the final step, counting these individual bright regions to quantify the result.
After creating binary mask, we have successfully isolated all the potential bits, but we still don't have our final number. To get this count, our algorithm employs a powerful computer vision technique called connected component analysis. The algorithm scans the processed mask and identifies every missing group of connected green pixels, essentially finding each separate island of signal. It then assigns a unique numerical label to each one. The total number of unique labels found becomes our final bit count. We do have to make one small correction. The algorithm also labels the entire black background as a single component. So we simply subtract one from the total to ensure we are only counting the bits themselves. With this precise count, we now have the quantitative data needed to classify the sample.
And to ensure our algorithm was both accurate and reliable, we performed a crucial calibration step. The most critical parameter is the beat minimum intensity, and to find this optimal value, we use the comparative histogram analysis. The image you see here is the key to our method. The red curve represents the negative control, an image with no target biomarker. This gives us the perfect fingerprint of the system's baseline background noise and other fluorescence. The blue curve is from our actual sample and it contains both that same background noise and critically the signal from the fluorescent beads. The K inside is defined where the sample signal rises above the noise floor. You can see the blue curve has a long tail of brighter pixel that is completely absent in the red negative control. This tail is our signal. The optimal threshold is therefore the value that best separates the noise profile from this true signal. As you can see, a value of 262 sits perfectly at the point where the negative controls distribution ends. By setting our threshold here, we can confidentially ignore the vast majority of background pixels and focus on only the pixel that indicate a positive result. This data-driven method ensures our system is precisely tuned to characteristic of the assay.
After using histogram analysis, to set our optimal intensity threshold, we run the algorithm on our entire 18 image calibration set. This process provided us with a precise beat count for each sample of known concentration. The final phase of our collaboration was to analyze these counts to establish our diagnosis thresholds. By observing the clear separation in beat counts between our non-negative and positive samples, we were able to define the ranges that correspond to a clinical result. As this diagram shows, we set our negative threshold at 520 beats and our positive threshold at 3,400 beats. This creates a simple, data-validated framework for any new sample. A count below 520 is negative, a count above 3,400 is positive, and anything in between is flagged as low concentration. This final step completes our algorithm's journey, turning a raw image into a calibrated, meaningful diagnostic conclusion.
All of the complex steps we have described, from pre-processing and thresholding to continuing coding and classification, have been integrated into a single, easy-to-use application. To bring our Python algorithm to life, we use the Ginter library to build a graphical user interface, or GUI. Our tool allows a user to easily input the calibrated parameters we determine from our dataset. User first selects a negative control image to establish the system's baseline noise profile. Then, with a single click, they can select a sample image to analyze. The application automates the entire workflow in the background and within seconds presents a comprehensive report. This report not only gives the final positive or negative verdict, but also displays the original and processed images alongside the comparative histogram, providing full transparency and allowing for expert review. This tool effectively transforms a complex, multi-step image analysis process into a fast, repeatable, and accessible diagnostic aid.
Our project's ultimate goal was not just to create a software tool, but to envision a complete low-cost diagnostics system that could operate right next to a microscope. The ideal hardware for this is the Raspberry Pi, a small, affordable, and powerful single-board computer. However, moving our algorithms from a high-performance PC to the resource-constrained environment of the Raspberry Pi presented a significant engineering challenge. We had to carefully optimize our Python code, ensuring it could run efficiently without sacrificing accuracy. The biggest hurdle, however, was our remote internship. We couldn't physically connect to the Raspberry Pi to the lab microscope. Our team adapted by innovating, using a Raspberry Pi with 8 GB RAM at my home. We collaborated over video calls to deploy, test, and refine the application together. This experience was a fantastic lesson in real-world hardware deployment and creative long-distance teamwork.
And with this, we conclude our final presentation. In this presentation, we explain our algorithm, its working principle, specific properties, and the detection process. It was a huge pleasure for us to advance with an SI physical system, and we also owe our mentor Gamze a lot of gratitude for tirelessly helping us develop our system and find answers to our ceaseless questions in each of our meetings. Hopefully, we will be able to bring our work into a way that it will serve to more advanced and beneficial purposes in the future. Till that time, thank you for listening and take care of yourself. ELE 04 out.